Greetings! In this video, we'll be talking about AP Chemistry's topic 7.1, Introduction to Equilibrium. Equilibrium has to do with not having equal amounts of substances, but having equal rates of the production of products in a process and the production of reactants in a process. In other words, if you have substance A that is becoming substance B, but substance B also is capable of becoming substance A, equilibrium refers to the point where substance A's rate of becoming substance B is the same as the rate as B is becoming A. In other words, the rate of the forward reaction equals the rate of the reverse reaction. And so in equilibrium, it's not that we have equal amounts of A and B, reactant and product. We just have the rate going in both directions exactly the same. And this is called a dynamic equilibrium. Dynamic equilibrium is just referring to the idea that we don't have, once we reach equilibrium, A and B don't stop reacting. They continue to react. A is going to continually become B, but at the exact same moment, B will be becoming A also. And if those rates are equal, then you're not actually going to see a change in the amount of A present in your reaction vessel or the amount of B present in your reaction vessel. Both of them are going to appear constant, that their amounts are the same. And the amounts are the same, but it's still actually reacting. Particles of A are reacting and becoming particles of B. Particles of B are becoming A. So some physical and chemical processes that this could happen in is phase changes. If you are at the melting point of a solid, the solid is becoming the liquid, but the liquid is also becoming the solid at the same time. You create an equilibrium at that melting point. So phase changes can have equilibrium. Dissolving gases. If you have a solution that has a gas dissolved in it, like a soda, inside that can of soda, gas is constantly coming out of the solution, but also being redissolved back into the solution. So dissolving gases and undissolving gases. Dissolving precipitates. So if you have a precipitate present in a solution, the precipitate is redissolving back into the solution at the same rate that the solution is precipitating that precipitate out. Acid-base reactions, or just acids and bases in solution, like weak acids and weak bases. The molecules of the acid or the formula units of the bases are dissolving in the water and also coming out of the water. So you have this constant equilibrium being set up in acids and bases. And redox reactions also. A good example of this would be like a battery. Batteries set up equilibriums where electrons are coming off of half reactions and also being reabsorbed by half reactions. So you can have both directions on that. And I just realized I had music on. Okay, music is off now. Okay, so different processes that set up equilibrium are these. One way that we can represent equilibrium reactions is by graphing the concentrations of the reactants and products. And so I want to give you 4 examples of graphs that show what's going on in an equilibrium. So we'll talk about each one of these, and then that'll be it for today. So let's say that we have substance A becoming substance B, and it sets up an equilibrium. So B also is becoming substance A. If you'll notice on the y-axis, I have concentration, and A I've done in red, B I've done in blue. Initially, I have no B present. I have only A present. As the reaction takes place, the concentration of A is going to decrease because you're using up A. B is going to increase as the reaction goes along. So you're going to see an increase in substance B. Eventually, you'll notice we reach a flat line of both A and B at this point right here, roughly. At that point, we've reached equilibrium. In other words, the rate that substance B is forming is the same rate that substance A is disappearing. So even though we still have the reaction taking place here, the concentrations remain constant because the rate forward equals the rate reverse. Everything before this has to do with kinetics, has to do with the rate of reactions. And if you'll notice, the slope is decreasing because the rate is slowing down. Also, this is a 1-to-1 ratio. So for every mole of A that disappears, 1 mole of B is going to appear. So you'll notice that these slopes are identical, but just inverses of one another. Also, we can tell from this graph that this reaction is product favored. We've made more product than we kept reactant. So this reaction actually is going to lean more towards the product side than the reactant side. So a lot of things we can tell from this graph as the time goes along in the reaction. So let's go ahead and take a look at number 2 here. In number 2, we have 2A becoming B. It's an equilibrium reaction, so that means A is becoming B, B is also becoming A. If you'll notice, the slope of A is much more dramatic than the slope of B, and that's because it's a 2-to-1 ratio. So the slope of A is going to be twice the steepness of B at any given point. They're inverses, one has positive slope and one has negative slope because one's disappearing and one's appearing. But we can tell that the ratios are not the same, the mole ratio, the stoichiometric ratios, because the slopes are different. We can also tell where equilibrium occurs. It's where both lines are now flat, which is about roughly right there. So this is equilibrium over here. And this is product favored again, because B has a higher concentration than A at equilibrium. So this is a product favored reaction, meaning that the reaction is going to make more B than A remains. So that is our second reaction, our second graph. Our third graph, let's look at this third graph. We have A becoming B again in a 1-to-1 ratio. And notice that the slope of A going down is the same as the slope of B going up, just negative versus positive, because it's a 1-to-1 ratio. But notice this time we have a lot more A at equilibrium. Here's where equilibrium would be. We have a lot more A at equilibrium than we have of B at equilibrium. What does that mean? Well, that means that this is a reactant-favored reaction. In other words, the reactants do not become products as much as they stay reactants. So this is a reactant-favored reaction because we can see the amount of reactants is much higher than the amount of products once we reach equilibrium. And in our fourth graph, we have A becoming B again, and B, of course, in the reverse direction, becoming A. And if you'll notice, A is decreasing, B is increasing. We've reached equilibrium about right here, but then something happens. At this point right here, there's a dramatic decrease in substance A. And what that means is, all of a sudden, I have removed substance A. I've taken away some of substance A at equilibrium. So if I remove substance A, if you've learned about Le Chatelier's principle already, removing substance A means that we need to replace the A that we removed. So B is going to start making more A to reestablish equilibrium because we've disrupted equilibrium. So we removed A, B is going to start making more A again, so the concentration of A is going to start increasing again. And since B is making more A, we're going to lose some of B. And so you can see a decrease in the concentration of B at that point. So again, we can see these jumps once we reach equilibrium and be able to tell what's going on in the process. We lost some A, we removed it all of a sudden, and then it got replaced as B shifted equilibrium from the product side to the reactant side. So that's just a brief introduction to what equilibrium means and the definition of equilibrium. The key thing about equilibrium, though, is that the reactants and products are still reacting once you've reached equilibrium. It's just a matter of the rates being equal to one another. If you have any questions about any of this, please let me know. I'd be happy to help you out. Good luck.